Greetings, YouTube. Beautiful Mind here. So I realized that like with the last presentation that I did, we had like this echo thing going on. I didn't realize it until like after like an hour and 20 of streaming. I was like, yeah, I'm not about to do that again. So I'm gonna have to. I mean, I probably will go back and like make sure that the audio's fine, but uh, doing the best that I can to. Let's see. Yeah, I think that's fine. Okay. All right, so I think it should be okay. It looks okay. I don't hear the echo this time. So, but yeah, okay. So this presentation will serve as the lecture for week 7 Wednesday for Calculus 1 for spring of 2020. One, I hope that everyone is doing well. We're entering the home stretch. I think I went on and loaded the remaining assignments for the rest of the quarter on Pearson. You can actually go back to any assignment, old assignments, any assignment that we've done the whole quarter. You get unlimited attempts at them. For any assignment that's submitted late, I reduced the late penalty from 20% to 10%. So if you really wanted to go back and get an A on any old assignment, you can. Also, we need to be sure that on Moodle, let me say a few things. One, we need to be sure that we have an assessment that we're doing, so make sure that we're doing that. Be sure that you've completed the participation and honesty quiz. Yeah, I can't think of anything else. There's also the student evaluations, right? So those are available. So be sure to do those. Those are available via email. Okay. So yeah, I don't really want to go beyond section 5.3. We need to go like integration is like the other half of calculus, but because we're like on a quarter system, that kind of like, we just don't really have the time. But that's why at least I wanted to introduce this idea, this notion of integration. It's very important in calculus, and we really only have about like half of what we really need for calculus. Like we've talked about differentiation, and so like integration is like the reverse of that. So like given a derivative, how can we find the original function of, hopefully you guys can hear me. I'll do the best I can to go back because I just realized I didn't have the microphone there. Man, I've been having like audio issues like left and right, but that's how it goes sometimes. But yeah. Yeah, so integration is the reverse of differentiation. So given like a derivative, how can we get a sense of the original? And so we see in a graphical sense, that's going to be the area under the curve of the graph of the derivative. So we're going to explore ways of calculating the integral. Okay, just like how we had shortcuts for differentiation, there are like shortcuts for integration, like doing the reverse. Sorry. I don't know if you like ever like rub your eyes. Like it's so soothing. I'd be like ready to go to sleep when I do that. So that's what I was doing just now. Like my eyes, I was just rubbing. I was like, and it's just like it just makes me like so sleepy. It's really interesting. All right, so let's take some time. We'll do the best that we can with section 5.2, and we're going to look at definite integrals. Yeah, okay. So we introduced Risson sums in section 5.1 as a way to approximate the area of a region bound by a curve. Can I come on. I need you to work. Come on. There it is. I was adjusting the crop. There we go. That looks better. Okay. So we use the Riemann sums as a way to approximate the area of a region bound by a curve and the x-axis. In that discussion, we assume the f to be non-negative on the interval. Our next task is to discover the geometric meaning of Riemann sums when f is negative on some or all of a closed interval AB. Once this matter is settled, we proceed to the main event of the section, which is to define the definite integral. Okay, with definite intervals, the approximations given by the Riemann sums become exact. Okay, so we have this example, we have this notion of net area. How do we interpret Riemann sums when f is negative at some or all points on the closed interval AB? The answer follows directly from the Riemann sum definition. So we have this example 1, interpreting Riemann sums. Evaluate and interpret the following Riemann sum for f of x equals 1 minus x squared on the closed interval AB with n equally subintervals. The first part we want to do a midpoint Riemann sum where AB goes from 1 to 3 and n is 4. And then we want to do a left Riemann sum where AB is equal to 0, 3 and n is 6. Okay, let me see if we can kind of recreate what we did last time. Okay, let me do this and this. Okay, and let's do like this. That's fine. Let's see. So we have this f of x equals 1 minus x squared. Now you think of it in a graphical sense from college algebra. Notice that the highest exponent is 2. So we're dealing with a parabola. Can you tell me the sign? I want you to think for a moment, what's the sign of the leading coefficient? The sign of the leading coefficient here is negative because you want to put it in descending power order. So we should have a downward facing parabola, right? It opens down with a y-intercept of positive 1. So like if we take a parabola in a regular position, it's like we flipped it top to bottom and then just moved it up by 1, right? That's all that we did. Okay, so first we're actually doing a midpoint Riemann sum going from 1 to 3 and n is 4. Okay. So we want to break this interval up into 4 subregions. So notice that that distance is what, 2? So then if we say 2 divided by 4, that's a half. So we want to go from the first subinterval, we want to go from 1 to 1.5, right? That's the first interval. Then we want to go from 1.5 to 2, and then 2 to 2.5, and then 2.5 to 3, right? Those are so breaking that interval from 1 to 3 up into 4 subintervals, we get this. And it says we want to do a midpoint Riemann sum. So halfway between 1 and 1.5 is 1.25. So then we want to do f of 1.25 times the width of this is basically, we're finding the area of rectangle. So we're saying length times width. The width of this region is what, a half. So 0.5, right? So we have the length times the width based on the midpoint. So then this is going to be, what's f? Okay. So 1 minus 1.25 squared. And then whatever the answer is, we're going to say is times 0.5. I'm just going to use my calculator. I'm not going to show it because I don't feel like you need to see this done in the calculator. Like I feel like you can handle this. You should be able to handle this. Submit. Let's do a new right here. Thank you. I don't have to load that again. Okay, it looks good. Okay. I'm just going to go to my y equals. I'm going to type in my f of x. So my f of x is 1 minus x squared. Okay. I'm going to quit. Variables. My variables. So when x is 1.25, and over here we need parentheses like that, right? So let's say that times 0.5. So I get that this is approximately negative 0.28, okay? So then if we do halfway between 1.5 and 2 is 1.75, so we want to do f of 1.75 times 0.5. 1.03 approximately. 1.03, okay. And then halfway between 2 and 2.5 is 2.25. So we're going to do f of 2.25 times 0.5. And that's going to be approximately, I'm just using my calculator. So if we want to do 2.25. Okay, and then we want to do f of 2.75 times 0.5. 3.28. Okay. So, let's see. So if we think about the rectangle created by the midpoint of this segment and the y value, we get it as negative value, so we would just take the absolute value of each one, right, and add them up. So we're going to do 0.28, 0.28 plus 1.03 plus 2.03. That's not a 2.03. Plus 3.28. Okay. So I get the area under that curve is approximately 6.62. So these add up to, the absolute value of those adds up to about 6.62. Okay, I'm going to let that be for part A. That was example 1A. Okay. A left Riemann sum from 0 to 3, and we want to do 6 subintervals. Okay. So 3 divided by 6 is still a half. Okay. So example 1B, we need some more space. So then for example 1B, we want to go to from 0 to 0.5. That's the first one. And then 0.5 to 1. And then I think the rest are the same. Oh, left Riemann sum, okay. So we do have to adjust a bit. Oops, I missed one. Just copy it. Right there. Okay. And the original, let's just get a copy of that as well, right here. Okay. So we're asked to do this one with the left endpoint, okay? So we're going to say f of 0 times 0.5. So that one's just going to be 0.5, right? Okay. And then the next one is f of 0.5 times 0.5. Oh, sorry. Let me do this one first. Uh-oh. Okay. Okay. So this one is 0.375. 0.375. Okay. The next one, we want to do f of 1 times 0.5. Oh, 0? Should be 0, right? 0. Six o'clock on the dot. Doing my homework. So we want to say f of 1.5 times 0.5. So this one is negative 0.625. Okay. Okay, so f of 1 is 0. Okay. So then the next we want to say is f of 2, 2.0. So if we did f of 2 times 0.5, we get a negative 1.5, and then let's go ahead and do the 2.5. So then if we did f of 2.5 times 0.5, negative 2.625, okay? If we add up these absolute values, let's see. We're going to add up the absolute values. 0.5 plus 0.375 plus 0 plus 0.625 plus 1.5, 2.625, 2.625, okay. 5.625. So then these add up, the absolute value of these adds up to approximately 5.625. Okay. Let's see how do we do with these. Let's see how do we do. So the first one we got 6.62 and then 5.63. Okay, 6.63, let me see. Yeah, that's fine. Because of the rounding, but yeah, that's fine. And then for B, to calculate, we set the resulting Riemann sum are these. Set the final answer. .875. So let me see. Area under the curve. Let me think about it. I thought we just add them together. Okay. It's negative. In this case, the values are non-negative and are negative for those where f is positive. We get the positive contribution, and where f is negative, we get the negative contribution to the Riemann sum. Okay, regions above the x-axis. Consider a region bounded by the graphic continuous function of xn. So the net area is going to be the sum of the areas that lie above minus. Okay, so we don't take the absolute value. I guess not. Huh, that's interesting. Okay, so it's going to be the net. So we need to keep those negatives. All right. Oh, and so the first one should have been negative 6.625. So we definitely need to go back, right? So we should have kept those negatives. So we're going to keep that negative. That's fine. You live and you learn. And then these, we should have also kept the negatives as well. And so instead of adding the absolute value, we're just going to add them up as they are. And I think we get the negative 3.875. Okay. You live and you learn. All right. Yeah. Okay. So what we learned from example 1, on the interval where the function is entirely negative, the Riemann sums approximate the negative area of the region bounded by the curve, right? And then, okay, let's look at this. It says right here, In the more general case that f is positive on part of AB, we get a positive contribution to the sum where f is positive and negative contributions to the sum where f is negative. In this case, the Riemann sums approximate the area of the region that lie above the x-axis minus the area of the region that lie below the x-axis. The difference between the positive and negative contributions is called the net area. It can be positive, negative, or zero. Okay. So consider the region bounded by the graph of a function and the x-axis between x equals a and x equals b. The net area of R is going to be the sum of the areas of the parts of R that lie above the x-axis minus the sum of the areas of the parts of R that lie below the x-axis on this interval. Okay. And n goes to infinity of that. I just want to do integration. I'm tired of the Riemann sums. Okay. But yeah, that's the gist of it, right? So we pretty much take what we did last time, and now if we get negative results, we just keep the negatives, right? So that means we're talking about regions that are below the x-axis, and we take that as is. Okay, let's keep it going. Okay, we're gonna let that be. Okay, so this notion of the definite integral, let me see. A function f is defined on a closed interval AB is integrable on AB if the limit as the change in x as the change goes to zero. So you know, in these examples with the Riemann sums, we set like we'll have our change in x, right? I think in the last example, the change in x was what, a 0.5 for every subinterval. So as that change in x gets smaller and smaller and smaller, we get a better and better approximation for the area under the curve. So now this is saying let that change go to zero for these partitions. If it exists and is unique over all partitions of the closed interval AB and all choices of the x sub k star on a partition. This limit is a definite integral of f from a to b, which we write as this form. So the integral of f from a to b, you know, is expressed in this form. Let me see. Okay. Let me see here. Let's look at this notation really quickly. The notation for the definite integral requires some explanation. There is a direct match between the notation on either side of the equation in the definition of figure 5.21. In the limit as the change goes to zero, the finite sum denoted by summation becomes a sum with an infinite number of terms denoted as the integration. This integral sign is this guy here. Is an elongated S for sum. Okay, I never knew that. The limits of integration A and B and the limits of summation also match. The lower limit of the sum k equals 1 corresponds to the left endpoint of the interval x equals a, and the upper limit of the sum k equals n corresponds to the right endpoint on the interval x equals b. So the function on the integral sign is called the integrand. Okay. Finally, the differential dx in the integral, which corresponds to the change in x sub k, is an essential part of the notation. It tells us that the variable of integration is x. Okay, so we integrate with respect to that dx, right? The variable of integration is a dummy variable that is completely internal to the integral. It does not matter what the variable of integration is called as long as it does not conflict with the variables that are in use. Therefore, the integrals in figures 5.22 all have the same meaning. So in the first one, we're integrating with respect to x, with respect to omega, with respect to s. Okay, this is fine. All right, let's see this in action. I want to kind of work an example. So integrable functions, if f is continuous on a closed interval AB or bounded on a closed interval AB with a finite number of discontinuities, then f is integrable on AB. Let's look at this example. So identify the limit as a sum. Assume that the limit as the change in as delta goes to zero of this is the limit of a Riemann sum for a function on 1 to 3. Identify the function f and express the limit as a definite integral. What does the definite integral represent geometrically? So the definite integral should be the area under the curve produced by this function, right? Okay, so it says identify the function f and express the limit as a definite integral. Let me see. Is the limit for a function on 1 to 3? Okay, so in my mind, the first thing that comes to my mind is that I see now. I don't really want to try to use those forms that we used last time. We typically, I don't really recall using whatever forms we used at the end of last time. Those were just like for introductory purposes, in my opinion, to talk about the Riemann sum. I'm going to do this by integration. Let me see. Let me see something. Delta K, so that's like our dx. I am going to, I'm just going to do what I see, right? So, as that change goes to 0, so this should be like the integral. Let me see, our a, it should go from this. Is that 1 to infinity? 1 to 3, right? So it looks like we're integrating from 1 to 3. Let me make sure I'm interpreting this properly. Okay. Let's keep going. So then it looks like it should be like 3x squared plus 2x plus 1. I think I need to write it like this, dx. An f. Let me think about it. I feel like, okay, if I try to do what we did last time, you can like you should be able to break these apart because we had the power function last time. So x squared, we had a way to reduce that. We had the x sub k. The last two terms are they're actually okay. I'm not sure. Let me see, because this is where I was going, but we haven't talked about all the nuances of this. So I'm pretty sure they want us to do it the way we did it last time. I'm going to look at the answer for the sake of time. Let's see. We see that this, okay, that's fine. Because it's a polynomial, it's continuous, and therefore it's integrable. That's fine. We got that. Because this is positive, the definite integral is this. Okay. So what we had was actually fine. 1 to 3, 3x squared plus 2x plus 1 dx. Yeah, okay, cool. So I'd be like second guessing myself. This is why I encourage you all to not second guess yourself. Go with your first mind. Okay, I'm going to let that be. Yeah, I'm going to just let that be for right now. Okay. So that was example 2. Let's look at example 3. It says, use familiar area formulas to evaluate the following definite integrals. I really want to get into the shortcuts. I'd rather just do the shortcuts. But so for instance, if we're looking at part A, okay, it says use familiar formulas. So example 3A, right? We have the integral from 2 to 4 of 2x plus 3 dx, right? So if we were to look at the graph, 2x plus 3 is a straight line. Let's just look at it really quickly. I'll do a rough sketch. I'm really trying to. The y-intercept is 3, so let's just say this is our y-intercept. The slope is 2, so we have this, and we want from 2 to 4. So up 2 over 1, up 2 over 1. Let's do one more, up 2 over 1. So from 2 to 4, we're talking about this part here. Right, and we want the area under the curve, so I'm going to use this. All right, so basically we want the area of this region here. Let me do this really quickly. Go like this, like this, like this, like this. I do almost. here, 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 here. Nope, that's not what I wanted. Undo. Okay, that's better, yeah. So you can go there, you can go there, you can go there. You actually are supposed to be there, and you can go like, okay, we'll go style. All right. So we want the area of that shape. That's going to be the area under the curve, right? So you can like look at you can see the basic shape. I'm going to break it into two basic shapes. Right, so we can do the area of that triangle and the area of that rectangle, right? So if we focus on that triangle, area of a triangle is going to be 1/2 the base times the height. So in this context, it's going to be 1/2. The base we see is 2, and the height is, because it makes a right triangle, 1, 2, 3, 4. So it should be this, right? This is just that triangle part there, and that's going to be 4 square units. Area of the rectangle is length times width. So what is that? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 7 times 2, which is 14. So then we add those two together. So the area under the curve should be 14 plus 4, which is 18. That's just using formulas that we know from the past. Like, that's not really using the shortcuts that I'd like to. Let's see, we got 18 units squared there. I'm going to look at the answer to make sure that we're thinking about this properly so we don't waste a lot of time. It's a trapezoid, right? Okay, 18. 18 was good, okay. Ugh. So then for B, we're talking about the integral from 1 to 6 of 2x minus 6 dx. Okay. So again, that's going to be a straight line from 1 to 6. So let's just do a rough sketch again. The y-intercept is going to be what? -6. So let's move this like up some. Let's see, we got 1, 2, 3, 4, 5, 6. So here's our y-intercept here. And then the slope is 2, so up 2 over 1, up 2, there's, let me see, there's 2, 3, 4, 5, 6. And if we're going from 1 to 6, so we're talking about from here to here. Okay. So then we have the two regions, right? We have the negative region. So we have this region. And then we have this region. Okay. So we have the positive contribution minus the negative contribution, right? So if we focus on the positive, no pun intended, area of the triangle is going to be 1/2 the base times the height. So that's going to be 1/2. The base is what, like 3? And the height is 1, 2, 3, 4, 5, 6. So that's going to be what, 9. The negative contribution, again, if we say 1/2 the base times the height, that's going to be 1/2. The base in that case is 2, and the height is 1, 2, 3, 4. So that's just going to be 4. So then we're going to say the positive part minus the negative part. So then ultimately the area is going to be the 9 minus 4, which is 5. Okay. 5 units squared. Okay. I think I'm gonna just leave, just for the sake of time. I'm gonna leave the next one as like an exercise. You can use transformations to graph it, and then I'm just for the sake of time, I'm gonna leave that one though, because the idea is there. Let's see. 5, right, is what we got. Okay. Semicircle, right? I'm gonna let that be. So it says figure 5.28. I think we need to pull up that figure. Let me go ahead and do that now. Okay. Copy. Paste image. Then want to crop. Okay. Moving kind of slow. Come on. Okay. All right. So figure 5.28. Let's get some space. Figure 5.28 shows the graph of a function f with the area of the regions bound by its graph and the x-axis given. Find the values of the given following definite intervals. Okay, let's see. Let f of x. Nope. Oh, okay. So for the leftmost part, the area is 12, the middle part is 10, and the right part is 8. So from A to B. Okay. All right. Ooh, give me just a moment. I'll be right back. All right, and we are back. Okay. So right here, we have example 4a, and we're asked to evaluate. We have the integral from a to b of f of x dx, right? Okay. So from a to b, so let me see, a to b is just the green part. So that answer is just going to be 12, right? And then for b, we're asked for the integral from b to c of f of x dx. B to c is just going to be 10. The integral from a to c, f of x dx. A to c. So we got to say the positive contribution minus a negative contribution. So it's going to be 12 minus 10, which is 2. And then 4d. From b to d. f of x dx. Dx from b to d. B to d, so it's basically, it should be 8 minus 10, which is negative 2. All right, let's see how do we do. That wasn't too bad. 12, 10, 2, negative 2. And we can actually get that on one page. I'm gonna shrink this down. I don't think it's too terribly hard to follow. Okay. I feel like we can get some more space too. If I move that there, if I move this next to it, and then stack them, I think we can get it a little bit bigger. Okay, that's a little bit better. So then let me get rid of this guy. Okay. 12, 10. Let me reverse those orders. So put you, I guess we'll put you here. And then you can go beside him. Then we're gonna take both of you guys. Put it like that. There we go. I feel like that's a little bit better. Okay. So then 12, 10, 2, and negative 2. Example 4. 12. Oh, the negative region tag on it. Yeah, that totally is negative 10. So this is going to be negative 10. Two and negative 2. Okay, that's fine. Okay, reversing limits, right? So, man, this Google thing is listening hard. Just because I said okay, it was like ready to go. So if we have the integral from b to a of f of x dx, if we reverse that, the limits of integration, then it's going to be negative the integral from a to b. And then also note that the integral from a to itself is kind of like a point, so that the area under that curve is going to be 0. I'm going to let that be. We have the integral of a sum, we can rewrite as the sum of the limits. Okay. You see the explanation there. Constants and integrals. So if we have the limit of a constant times a function, we could say it's the same as the constant times a function. Sorry. The integral of the constant times the function is going to be the same as the constant times the integral. Okay. If you have a subinterval like for the point interior, so like on the left, if we have the integral from a to b, if we have a point P that's between a and b, then you could say the integral from a to p. So the integral from a to b is going to be the same as the integral from a to p plus the integral from p to b. All right. All right. Properties. So let's see. Let's kind of mention this really quickly. So the integral from a to itself is going to be 0. The integral, say we have the integral from b to a, and we reverse the order. So the integral from b to a is the same as negative the integral from a to b. We have the sum. The integral of the sum becomes the sum of the integrals. The integral of a constant times a function becomes a constant times the integral. Let's see. If we have some point between a and b, the integral from a to b can be broken apart into the integral from a to p plus the integral from p to b. Okay, I'm gonna let that be. Ooh, getting sleepy. What time is it? How much time? We've been going for 45 minutes. We're almost done. We're not. Yeah, I think we got 2 more examples. Okay. Assume the integral from 0 to 5 is 3 and 0 to 7 is negative 10. Evaluate the following integrals if possible. Okay. So that's a little bit of foreshadowing that maybe some of these might not be integrable. Okay. So we have this example 5a. We have the integral from 0 to 7 of 2 times f of x dx. Okay. This should be the same as 2 times the integral from 0 to 7 of f of x dx. But then 0 to 7 of f of x is going to be negative 10. So this is going to be negative 20. Okay. B asks us to do the integral from 5 to 7 of f of x dx. Zero to 5, 0 to 7. So notice that 5 is between 0 and 7. So what should be the case, the integral from 0 to 7 of f of x dx should be the same as the integral from 0 to 5 of f of x dx plus the integral from 5 to 7 of f of x dx. So then we can use this to isolate the integral from 5 to 7. So then ultimately, the integral from 5 to 7 of f of x dx should be the integral from 0 to 7 f of x dx minus 0 to 5 f of x dx. Okay, let's see. Okay, if we keep going with this notion, 0 to 7 is negative 10. So it should be negative 10 minus 0 to 5, which was 3. So it looks like that area is going to be negative 13. We're just going to go with it for now. We'll check it momentarily. So example 5c. Man, I feel like we're just gonna be getting to the good stuff. I might continue to do some lectures, but not make you responsible for it. Like, I want you to get practice. You should have a book if you want. You know, if like after we finish section 5.3, if you want me to make some more, like do some more lectures, I'm open to it, because this is actually like really important for calculus, and it's really interesting, and it's fun. I really only want you to be responsible for up to 5.3, but if you want me to do like a lecture or two beyond 5.3, I'm open to keep going. If anybody requests it, I'll make more videos. If not, I won't worry about it. Just because we really are out of time, and I don't want to give you more work. I feel like you have enough for the quarter, but this is like a very important topic, and it's a lot of fun. Like, I enjoy it, but again, because we're on a quarter system, we just don't have the time. Give me just a moment. All right, and we are back. So for 5c, we're asked for the integral from 5 to 0 of f of x dx. So let's get some more space. So we're asked for the integral from 5 to 0 of f of x dx. Well, that should be the same. If we reverse, it should be negative the integral from 0 to 5 of f of x dx. 0 to 5 was what, 3? So that should just be negative 3. D 7 to 0. They should be similar. So that one should be 10, and then E. 0 to 7. The vertex, okay. 0 to 7, absolute value of f of x dx. Let me go back and see what did it say about absolute value. Is the sum of the areas is there a property that we can use? I'm just going to take that one. I think that was just going to be, I think that was just 10. Because y is not allowed to go negative there. So it's forced to be positive. I'm going to go with this. Let's see how do we do. So we do have an extra page again. All right, let's see how do we do. So the first one we got was what, negative 20. Then we got negative 13. Then we got negative 3, 10, and 10. Uh-oh, looks like we made a mistake. 60, 06. Did we miss one? A, B, C, D, D. Let's go back to D. Oh, we did miss that 6. So we had 7 to 0. There's a 6 in there, so we just didn't see the 6. So let's do like this. There's a 6, not there. D, right? There's a 6 here. So this needs to be 60. I think that's it there. Okay. So that yeah, that one was a trick and I got it wrong. So we definitely got that one wrong. I'm gonna just cross to this one. I was just wrong. So it can't be evaluated without knowing the intervals in which f is positive and f is negative. It could have any value greater than or equal to 10. Okay, that's fine. Yeah, that's why I was hesitating on that one. I was like, but that answer makes sense. Okay, I think we have one more example. Yeah, let's just go ahead and do that example, and then we'll do some closing remarks for the day. Bounds on definite intervals, non-negative integrand. Okay, let's see what we have. We have a few additional properties. Let f and g be integral on the closed interval ab where b is greater than a. If f of x is positive or non-negative on the closed interval, then the integral is also going to be non-negative. If f of x is greater than g of x on the closed interval, then the integral from a to b of f of x is going to be greater than or equal to the integral of g of x. If f is bound between m and two different m's, then m times b minus a is going to, then the integral is going to be bound by m times b minus a and m plus, sorry, little m times b minus a and big M times b minus a, right? So this integral is going to be between those two. And the next section, property 9, is used to prove the central result of this chapter, the fundamental theorem of calculus. Okay. I think that's in the next section. Okay. Let's see. Find the value of this by evaluating a right Riemann sum and letting n go to infinity. A right Riemann sum. It's a cube. We want to go from 0 to 2. And n goes to infinity. So like, do they want us to take like several values of n? A right Riemann sum, so that means the x sub k, we got to say the a plus k delta x. N goes to infinity. That delta x goes to 0. Missing something there. I'm just going to use this one because we typically are not going to do it this way. Let me see. Based on an approximation found in example 5, the value of this interval is 6. That's fine. To verify this, we now evaluate the interval exactly. So the delta x is going to be b minus a over n, which produces the grid points. Delta x 0 plus k times 2 over n. A is 0, k is k, delta x b minus a over n, okay, is going to be 2 over n. That's fine. So then we get 2a over n, right? So then the x sub k star is going to be 2k over n, okay? Letting f of x be this, the right Riemann sum, okay? So this is from last time. Let me highlight this. So f of x sub k star, we have an expression. We have this expression here for x sub k star. So then that goes into our function. The 2k over n cubed is this. Delta x, we said it was 2 over n. We can distribute, that's a constant, right? So the constant went in front and they cubed, right? So we can move the constant in front of the Riemann sum. If we cube 8k cubed over n cubed, that's fine. Now, this isn't really distributing, but we can rewrite this Riemann sum in this fashion. The sum of the sum, we can write, that's not going to work here. But we can rewrite the Riemann sum in this fashion, right? Keep our parentheses. We can, let's see, the 8 can go in front because it's a constant. The 8 over n cubed can go in front because it's a constant. Then this becomes a power, the Riemann sum of a power function, right? This is going to be what? N here. I think we have an expression last time for the cube. So this is from last time, okay? Yeah. And I think we're actually okay. Then it's just a matter of just simplifying all of this. Let's see. We could distribute the 2 over n. That's going to be, let me see. We got an n to the 4. So the n's, let's see. We could expand that. This could cancel one of those. No, is that not working either? N cubed. Let's see. This can turn that, get rid of that. Okay. And we're going to distribute. Those are going to cancel. So the 2 makes sense. We're going to have an n to the 4 there. Seems like those would cancel. Oh, okay, I see. I guess. So yeah, we will have n to the 4 on bottom. That n to the 4 created by these two can cancel with this n squared, and we're just going to be left with the n squared on bottom. That's fine. Then if we expand this out and distribute a 4, 4 times that expanded thing is here, plus the 2. See, I would have tried to take that further by getting it into 1. Now evaluate this by letting n go to infinity. Okay. So as n goes to infinity, we could rewrite it, right? This goes to 1 because the powers are the same. This one is going to be 2 because there's no n there. Let me see. We can cancel. That'll be a 1. That'll go to 0. That'll go to 0. So with something like this, if I was evaluating as an n goes to infinity, I would distribute this n squared. I think this is okay to do. And so if we distribute the n squared, we're going to get 1 plus 2 over n plus 1 over n squared. And then as n goes to infinity, that 1 is going to persist. This is going to go to 0, and this is going to go to 0. So then we would get 4 times 1 plus 2 equals to 6. Yeah, we don't usually do it that way. I mean, again, to me, that kind of parallels the whole like when we were introducing the notion of derivative and we were using the difference quotient from like college algebra. But that was like, to me, that was way harder than like using the shortcuts for derivative. To me, this kind of discussion is similar in that regards. Whereas there are shortcuts that we use for integration, and there is nothing like this. To me, it's way easier. I think that's just to kind of like set a foundation and like to introduce and like to like prove some of these notions and ideas. But honestly, like because I was about to use the shortcuts today, I was like, no, I know we're not supposed to use it just yet. So I was trying to do it without using a shortcut. And to me, it's more challenging. Once you get the shortcuts, in my opinion, it goes a lot faster. Now, that's the whole shortcut thing is another discussion because there are like so many different techniques and types, and I really want to at least touch on them. I know we're out of time, but I really do want to introduce them because they're fun, like, and they're important, especially if you want to do any kind of like mathematics going beyond. So I want you to have at least have seen it. I know we don't have the time to go into details, but you know, we'll take whatever time. Again, now if anyone requests for me to just do presentations going beyond 5.3, we can. But I don't want you to be responsible for any more work beyond 5.3. So I think that was the last one for section 5.2. So let me do the following. Do like this. I'm gonna do it like this. Okay. All right. So that was our presentation for section 5.2, an introduction to the definite integral, and our next lecture for Friday, that'll be the end of the new material that we're responsible for. I think I did go ahead and load a final exam based on what we've done, basically the first 5 chapters up to 5.3, so in the very beginning up to 5.3, give or take a few sections, but it's based on the homework that we've done. I think I went on and loaded the final assignments. We have just under 2 weeks of time remaining. All assignments are due that Saturday, May 16th at 11:59 p.m. And then I think I went on and made the final exam available until our last class time, right? So our last class time is that Monday, May 18th at 2:50 p.m. right? So the final exam is at least available until then, but our homework assignments are due that Saturday before the final, all right? So I went on and made these things available because I just want you to take some time, have time, you know, and work on it. Okay. I can't think of anything else. You guys seem like you're holding strong for the most part. And just I'm available if you have questions or if you need support or anything. I'm available. On that note, we're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Peace.